This is what I call bridging the gap, and this will help us connect circular motion to linear motion. Our first attempt is to try to understand what tangential, oh boy, that's trash. Our first attempt is to try to understand what tangential speed is. And you know tangential speed, well, it's a speed, right? So if we're going to be careful about it, we're going to say how far you've gone divided by, that would be s for the edge of a circle. Let's just draw ourselves a circle over here and we can consider it while we're working. S is how far we've gone along the circle, and the time is going to be in the denominator. So let's consider one circular path that we can easily understand, and that would perhaps be starting here and going all the way around. So how long, what is the arc length if we go all the way around? Let's say this is a distance r. Well, it's going to be 2 pi times r. And everybody in 5th grade has learned that the circumference of a circle is 2 pi r. But what's the amount of time that it takes for something to go all the way around? That has a special name also. It's called period. So let's identify this a little bit more carefully. We're going to say this is r times this quantity 2 pi over period. You'll remember from a previous video that 2 pi over period is something. I'll give you a moment to think about what it is. Let's see, it has units of 1 over seconds, or maybe it has units of radians over seconds, because 2 pi really does look like radians. But remember, these radians are they're kind of like phantom units. They go away and they come back, and etc. So this is units of 1 over seconds. And it is, in fact, the same thing as omega. So we can now write down perhaps the most important equation from circular motion, that tangential speed is r times omega. And it's so good that I'm going to put it into a box. Watch this. Tangential speed is r times angular velocity. A box and a flower pot. That is a good equation right there. Let's think about what this means. This means that for a given angular velocity, your tangential speed will be greater if the radius is bigger. Sure, for an angular velocity of like 1 revolution per second, if the radius is out here, you're going to be going really fast to get all the way around. And if the radius is really small, you won't have to go very fast at all to get all the way around in 1 second. Tangential speed depends on radius in that way. Let's see how tangential speed depends on omega. This is also pretty obvious. If we have a given radius, if omega is big, that means we're getting lots and lots of revolutions in a second. Then we're going to have a large tangential speed. And of course, if omega is small, then we're not getting very many revolutions in a second, and the tangential speed will also be small. Let's go on and consider acceleration. We're on a roll, right? Let's consider the acceleration in a centripetal direction. And our book this year writes it as ACP. This is linear acceleration in a centripetal direction. And you know that something that's going in a circle has centripetal acceleration. And we saw that it's VT square over R. And I'm going to take this definition of VT up here and plug it in. If you don't believe this equation, I've got a video where I explain on geometric bounds how that actually makes sense. There are several other ways to see this as well, but I haven't gone into depth on those. But check out the videos, and other people have explained it probably much better than I have. Check them out too. Tangential speed is r times omega, and I need to square that sucker, so I'm going to get r omega, and I'll show you each step. Look at how kind I'm being today. This is r square omega square over r cancel, green. We have centripetal acceleration being r times omega square. Interesting. Put that in a box up here also. Centripetal acceleration, linear centripetal acceleration. I'm not talking about angular acceleration now. Linear centripetal acceleration is r times omega square. And I guess that means this must be instantaneous, because it depends on an instantaneous value for angular velocity. linear centripetal acceleration does not immediately depend on angular acceleration. It depends on how fast you're going angularly, not how much you're accelerating angularly. This is weird because this equation seems to be the opposite dependence on r as this equation for centripetal acceleration. See if we can make sense of that a little bit. This equation for centripetal acceleration says that this acceleration towards the center, let's say we've got something right here and it's accelerating towards the center. This equation says that the acceleration towards the center gets smaller as the radius gets bigger. Yes, and that's assuming that the tangential speed stays the same. If the tangential speed stays the same and I'm out here, then I don't need as much acceleration. But over here, to see how the centripetal acceleration depends on r, we're assuming that the angular speed stays the same. Now I'm talking about everything that's on this. And as I have a bigger r, I'm going to need more centripetal acceleration in order to stay moving in the circle because, as you can see, check this out, the further out you go, the faster your tangential speed is. Listen to that one more time if it didn't make sense. I'm trying to say this very carefully. If we're looking at this equation, we're holding omega constant and looking how centripetal acceleration depends on r. And the further out I am for a given omega, I'm going to need a greater acceleration to keep moving in a circle. This is a different effect than the way centripetal acceleration depends on r in this equation because we're holding tangential velocity constant. So we've got a couple more equations to consider. Well, let's just throw one more equation at you, and that is tangential acceleration. Tangential acceleration happens only when, well, let's see, tangential acceleration would be in a tangential direction, at, and that happens only when we don't have uniform circular motion. This, I'm going to write that down, that's very important. Only exists when not uniform circular motion. Cool. So we don't have any tangential acceleration if we're moving in a uniform circle. That means our speed is constant and we're staying at a fixed radius. This would only happen if we were speeding up or slowing down because it's acceleration in the direction of the velocity. So it's not just turning acceleration. It is, in fact, simply r times angular acceleration. So we've got all kinds of cool little equations that we can write down, and I'm going to try to summarize them on this page. The equations that bridge the gap are very important. So I'm going to write them down. Let's put them in black. Nice. Bold. Vt is equal to r times omega. At is equal to r times alpha. And in fact, there's a final equation that says that s is equal to r times theta. Look at these equations. See what a similar form they have? If you want to go from linear to, let me rephrase this. If you want to go from circular to linear, you need to multiply by r. For position, you take the angle, you multiply by r, and you get the arc length. For velocity, you take the angular velocity and you multiply it by r, and you get the tangential velocity, or tangential speed. And for angular acceleration, you multiply by r, and you get the tangential acceleration. Cool. One more thing that I want to put on here is the distinction between tangential acceleration and centripetal acceleration. ACP is r omega square, and AT is equal to r alpha. So tangential acceleration requires that we change angular velocity. This is the derivative of angular velocity. However, centripetal acceleration simply requires that we have an angular velocity. See if all that stuff makes sense to you. And you know, all the units for these things, this is very, very interesting. The units for alpha, let's say units for theta, or radians, or nothing. because radians are kind of also unitless. And the units for omega, radians per second, which is the same thing as 1 over seconds, because radians don't really exist. And the units for angular acceleration are radians per second square, and that's sort of the same thing as 1 over seconds square, because radians don't exist. I wanted to add one final thought on the idea of centripetal versus tangential acceleration. If you consider a body that is going around in a circle, maybe it's a dog on a leash staked at the middle right here. The dog might have well, certainly if it's going around in a circle, the dog is going to have a centripetal acceleration. So an acceleration that is pointing towards the middle. And the dog could, in principle, have a tangential acceleration in the direction that the dog is going. And that would mean that the dog is speeding up or slowing down. This should be horizontal, so I'll make it bold. Okay, perfect. So there could be acceleration that changes speed, or simply acceleration that causes circular motion, that causes that turn. And what I want to point out is that the full acceleration, the vector acceleration, then would be that tangential acceleration plus the centripetal acceleration. And so we can say, if we're interested in just how much the total acceleration is, we could make a right triangle here, and we could find that its components are the two accelerations. So we can use a little bit of Pythag and say that this is tangential acceleration square plus centripetal acceleration square. And we can even specify the angle of that, that relationship between these guys. So here, let's say that we're interested in this angle right here. This is the angle, we'll call it the angle phi. I'll call that out right there so that you can see it. That's the angle phi. And I can argue that phi is the inverse tangent of what? Phi is the inverse tangent of the opposite side, which is the centripetal acceleration, divided by the adjacent side, which is the tangential acceleration. And that tells you about the direction of the overall acceleration of the object. I hope that's making sense. Ask me a question if it's not. This quantity 2 pi over period. You'll remember from a previous video that 2 pi over period is something. I'll give you a moment to think about what it is. Let's see, it has units of 1 over seconds, or maybe it has units of radians over seconds, because 2 pi really does look like radians. But remember, these radians are they're kind of like phantom units. This is what I call bridging the gap. And this will help us connect circular motion to linear motion. Our first attempt is to try to understand what tangential, oh boy, that's trash. Our first attempt is to try to understand what tangential speed is. And you know tangential speed, well, it's a speed, right? So if we're going to be careful about it, we're going to say how far you've gone divided by, that would be s for the edge of a circle. Let's just draw ourselves a circle over here and we can consider it while we're working. S is how far we've gone along the circle, and the time is going to be in the denominator. So let's consider one circular path that we can easily understand, and that would perhaps be starting here and going all the way around. So how long, what is the arc length if we go all the way around? Let's say this is a distance r. Well, it's going to be 2 pi times r. And everybody in 5th grade has learned that the circumference of a circle is 2 pi r. But what's the amount of time that it takes for something to go all the way around? That has a special name also. It's called period. So let's identify this a little bit more carefully. We're going to say this is r times